A warm welcome to my dear students and friends. A very good morning, good afternoon, good evening to all of you, and welcome to this DADM, which is Data Analysis and Decision Making course under NPTEL MOOC series. And we are in the 35th lecture. So, as you know, this course is total duration is 12 weeks. So, this 35th would basically signify we are ending the 7th week, and the total number of lectures is 60 and total hours content is 30 hours, and each week we have 5 lectures and each lecture being of half an hour, 30 minutes. And I am Raghunandan Sengupta from the IME department, IIT Kanpur. So, if you remember, we were discussing about the, very briefly we discussed about the multivariate extreme value distribution, but it was not possible to give the example for a 2-dimensional or higher dimensional case. I took a very simple 1-dimensional multivariate extreme value distribution for the 4 indices in the stock markets, which is Nikkei from Japan, FTSE from United Kingdom, then Kospi from Korea, and Nifty from India. And I just drew or explained that how you can take the blocks for each some duration of time. The blocks can be overlapping also. You take the maximum or the minimum depending when you are going to for the positive returns or the negative returns. Take the maximum for each blocks and then concatenate it or do bootstrapping to increase the sample size, make it almost equal to the population, and do find out the average values for the sample means or the variances, whatever it is, and then find out in the long run the expected value of the parameter of the random variable distribution, which is basically a univariate case of the extreme value distribution for the maximum. And then from that you can find out the alpha, beta, gamma, which are basically, I am using the general symbol for alpha, beta, gamma, which is location, scale and shape, and then you can basically find out how the distribution looks like. Similarly, you can do it for the minimum also and do your analysis accordingly. Then in the last part, though very briefly I mentioned that given the multivariate normal distribution case, you want to find out the parameters. So, I said that, and generally this is a norm for the maximum likelihood estimation problem. You find out the corresponding probability, supposing that capital X equals to x1, capital X2 is equal to x2, capital X3 is equal to x3. Find out the corresponding probability, take the log and differentiate. So, the difference it will be partial differentiation. When I am using the word differentiation here, it is partial differentiation. Partial differentiation with respect to the parameters, put them to 0 and solve it. So, obviously, if they are closed form solution, no problem, you will get exact solutions which are basically alpha hat, beta hat, gamma hat, or the location, shape and scale estimated value, and then you check the unbiasedness, consistency, and then basically proceed further. In the method of moments, you basically take a sample, find out the moments with respect to the parameter values, then equate it to the values which you have found. If you have, I have only dealt with only 2 slides there. So, equate it and find out the estimated values and proceed accordingly. So, this concept will be utilizing here also. So, once you have the log likelihood function, so log likelihood functions consists of something to do with the fixed values n and p, which p is the number of random variables we are taking, n is the sample size. Second term would be something to do with the variance covariance, and the third term would be the difference of x minus mu whole square transpose and all these things. So, basically the mean values on the variance covariance matrix. So, if you differentiate, these parameters are mean, which is mu 1, mu 2, mu 3 till mu p. Similarly, sigma 1 and sigma 2 would be the standard deviation. So, you take them accordingly. So, So, you basically partially differentiate with respect the log likelihood with respect to all the mean values. So, these are to be found out, these are the parameters. Similarly, you will differentiate with respect to the standard deviation of the ith and jth one, and take j is equal to 1 to p, j1 j2 is equal to 1 to p, find it out. So, once you find it out, you will find the hat values. So, these are the hat values. So, the mu hat would be equal to the sample mean for the first set of observation. Similarly, mu 2 hat will be the sample mean for the second random variable set of observation. Similarly, for the last one, which is mu hat suffix p, which is the sample mean for the pth observation. So, what you have is you have this observations x11. Okay, let me do it for the. I am going to consider this value, it will be easier for me to discuss. So, hope this basically signifies the bold. First readings, you should go to the pth reading 1, first reading, first random variable 2 to pth reading 2, first reading n, pth reading n. So, this is of values would be number of rows would be 1 minute. This I think I have not written it correctly. Wait, please. So, this is the first reading first reading second. I think I should redo it. Sorry, just if I am trying to utilize. So, it will be p rows and n columns. So, p rows. So, now it is right. So, this one. This is basically the first random variable for n number of readings, and similarly this is the pth random variable n number of readings. So, I consider from here the average. So, this is okay, my color scheme is different, sorry. So, it is easy to. So, if you take the average, it is 1 by n summation of x1 j is equal to 1 to n. Similarly, for the last one, so I am going a little bit slow, please bear with me. This gives me the averages. So, this average is done, average is done. Now, I want to find out. So, this is for the averages for the sample, remember that. So, this would basically come here. This I am using the red color. So, let me highlight it using the highlighted red. So, this would come here. Okay. Now, I want to go to the first part, which is the expected value for the population. This is for the mean for the sample. So, I will erase it. So, this I will highlight. So, these are the mean values for the sample. So, I will erase it again. I will again draw it, but using a different color, so it is not confusing for all of you. And okay, this I need to erase also this. So, this is done. So, now I use the pen of for example green color. So, consider coming to the variance covariance matrix. So, you have so this is the matrix which I have, same thing, but I am trying to basically give a different color. So, now, so say for example, I want to find the covariance of x I x j. So, I and j are basically changing from 1 to p. So, both values can be same or different. So, that is equal to the expected value x I minus mu I into x j minus mu j, and I have discussed this, that how you can find out using the joint distribution in the discrete case and the continuous case. I just discussed the formula. If you remember, those bullet points were there 1, 2, 3, 4, they were about 9 bullet points in one of the lectures. Now, in case if I is equal to j, you will have the variances, and in case that not I is equal to j, you will have the covariances. So, obviously, you will have the covariance variance matrix, which is this one. So, this is the covariance variance matrix. But now, in the case when you are taking the standard error square, so obviously, you will have so they would be given by the formula here. So, it will be 1 n minus 1, but why n minus 1? Because you are losing 1 degrees of freedom, summation of x I j 1 minus, this is suffix 1, x bar. So, I will take I as 1 to n, and I will basically change this to j 1 multiplied by x I j 2 minus x j 2 bar. So, these are the average values which I have already found. So, they are from here. You have already found, these are the values. These are the values which you are finding out. And once you find out, the formulas would be corresponding to this formula would be equal to the standard error whole square or standard errors corresponding to the fact that the mean value is not known. If the mean value is known, obviously in that case it would be n only, you are not to lose, and in this case obviously you won't consider this. So, this would become mu J1 bar mu J2, not bar, sorry, mu J1 and mu J2, which are the expected values. And corresponding to the case, the symbol generally denoted for the variance covariance estimate value would be S, the bold S, because there is a P cross. So, you can find them and then basically utilize them in your calculations. I went a little bit slow, so you could basically understand. Now, let us consider the few cases of hypothesis testing. Now, in the hypothesis testing, again I will recap. If you remember, in the hypothesis testing there are four types of problems, something to do with the mean, something to do with the variance, but under each mean and variance you have another two class. For the mean, you will consider in the first case the variance is known for the population. So, obviously in that case you will use the Z distribution. In the other case you will consider the variance is unknown. So, what you will do, you will replace the variance of the population using the best estimate from the sample, which would be S dash, because S dash basically means you have some information about the mean of the population. So, when you use S without the dash, you will use the T distribution with n minus 1 degrees of freedom. If you are trying to find out the difference of two means, provided the variance of both the populations are known, then you will use the Z distribution without any loss of degrees of freedom. But when you have basically the variances of both the populations are unknown and you want to find out something to do with the differences of the means, you will use the T distribution and the m minus 1 from the first case and n minus 1 from the second case. So, it will be m plus n minus 2. Now, when you go to do something with this, the variance, there are two different sets there. In the variance, if provided the population mean is known, then you will use the chi-square without losing any degrees of freedom, because in that case you are using the S dash where the population mean is known, and in case, and obviously degrees of freedom would be n. And when you are trying to find out something to do with the for the one population, when something to do with the variance of the population giving the mean of the population unknown, you will use the chi-square with n minus 1 degrees of freedom. Then if you switch on to the case of finding out the ratios of two populations, there would be two different instances or two different flavors. In the first case, the flavor is both the mean values are known, hence you use the F distribution with degrees of freedom m comma n, because of freedom, using the ratios of the variances, but the mean values are known, you will use the F distribution with m minus 1, losing 1 degrees of freedom from the first case, minus 1 losing 1 degrees of freedom from the second case. Now, if you remember, these distributions which you have considered, the counterpart in the multivariate case were the student T distribution for the multivariate case and wizard distribution for the chi-square. So, these concepts which we have used in the univariate case would be utilized in the multivariate case also. So, let me continue reading. Let us now suppose the few relevant results without proofs for the same can be stated as follows. Now, our case for, so they would be multiple cases, but we will go logically. So, we want to test the statisticity, the alpha betas, the type 1, type 2 errors concept would be there. The test statistics for H naught, given that here in this case you will consider mu under H naught HA, which is the alternative one, you can have greater than, less than, not equal to. So, obviously, if it is greater than, you will consider the right hand side, I am looking from my side, less than you will look at the left hand side, not equal to you will look at the middle range. Obviously, that is the upper control limit and the lower control limit. And remember again the same concept, that for the upper control and the lower control, when it is basically greater than less than, you will always use the suffix for the distribution, whether t or chi or f, it will be 1 minus alpha and alpha for the left and the right. When it is two sided, when you are using not equal to, it would not be 1 minus alpha and alpha, it will be 1 minus alpha by 2, that means alpha by 2, not the total value, and in another case it will be alpha by 2, such that the whole of area which you are going to cover from the leftmost to the rightmost would be 1, as per the concept that the CDA value is 1. The test statistics is, as I mentioned, for the H naught is A prime, A prime A transpose, where A is a vector. A transpose into mu is equal to A transpose into mu naught under H naught, and under the alternative one, it is A transpose into mu A, which can be greater than A transpose into mu equal to H A transpose mu naught, and would be less than equal to A transpose mu naught. So, 3 cases. So, if we have for the greater than type, you will have, I am just drawing the distribution on the right hand side, not equal to and great less than type. This is for this, this is for this, this is for this. So, given the variance covariance matrix, obviously variance matrix is known, then we need to find out the distribution of n into x bar into mu naught into the inverse of the inverse of the variance covariance matrix, that is equal to, and multiplied by x bar, which is the sample mean minus the mu naught under H naught, that is chi square distribution with p degrees of freedom, and the value of alpha would be decided accordingly, which is the level of confidence. So, in this case here I will use the different color, okay, I will use the highlighter. So, this area or this area and finally this area. So, these areas is equal to 1 minus alpha. So, this is alpha, this is alpha, this is alpha by 2, this is equal to 1 minus alpha, this area is equal to alpha, this is equal to, the whole area remains constant as 1. So, in the value of alpha, there is the level of confidence, problem formulation and the practical requirement, and you will basically solve the problems accordingly. Now, you will consider the test statistic considering the same thing H naught, where you have A transpose mu is equal to A transpose mu naught under H naught, and under HA alternate hypothesis you have 3 different flavors. First one is A transpose into mu is less than, the second case is A transpose mu is greater than, and the third case is A transpose mu is not equal to with respect to the H naught. So, less than, not equal to, greater than or with respect to the H naught. Now, in this case the variance covariance matrix is not known. So, if it is not known, you will basically use the S matrix. So, it matrix we have just done it. So, basically you lose 1 degrees of freedom in each of this reading when you are trying to find out the standard deviation square for x1 or x2 or x3, so on and so forth. So, that test statistic which is highlighted here is T distribution, this multivariate T distribution with T squared is 1 with p degrees of freedom, and the value of alpha and the practicalities, and we solve it accordingly. Now, the characteristics form of the T square statistic, this is not the T distribution, T square statistic, by the fact that if you remember, we take basically the case where it is not one to one similarly, but I am trying to basically give you some hint. So, in generally what you do, you basically find out x minus mu by square root of n. So, y square root of n, so that would basically be no, so same square, sorry. So, basically when I have the sample, it becomes this. So, now I will consider this. So, this. So, in this case I am taking the square. So, obviously it becomes x bar minus mu transpose into x bar into mu. So, you are basically going squaring this, which is right, and in the other case this standard deviation which goes up. So, obviously minus 1. What we have is the square root of n in the case with, obviously that would also go up. In the case it becomes with the minus 1 power. So, the stress statistics, few important points about the statistics are sample covariance matrix, and technically the properties are x bar n, which is the sample distributed with mean value mu, and the covariance matrix by n, which is the sample size. And if you remember, we did discuss about the chi-square distribution. In the same way, n minus 1 into s would be wizard distribution, which is distribution was the counterpart for the chi-square distribution with n minus 1 and the variance covariance matrix as the parameters. And finally, which is very important for the normal distribution, that for the univariate case also as well as the multivariate case, the sample mean and the sample standard deviation will be independent. This is not always true for the other distributions. So, I know that we are going a little bit slow considering the theoretical one. I will try to basically wrap up with a lot of examples in the later half. For any queries, whatever you have, please send us in the forum the queries, and we will try our level as fast. Have a nice day, and thank you very much.